Hello, we are lab4, group 4, and we're going to be talking about the System Identification Lab. First, an introduction. Quanser Incorporated has developed a new DC motor. They want us to create a controller for it. Quanser Incorporated has also provided a general model for the DC motor, without any known parameters. It is our job to determine these parameters for the DC motor and create a DC motor model that describes the Quanser motor accurately. We are also a group of engineers in the auto industry designing a robot arm to be used in manufacturing cars. The arm will be cyclically loaded under a variety of high and low speed duty cycles. We need to determine if it is suitable for the operating conditions given in case 1 and case 2. Case 1, where voltage is 2.3 volts and frequency is 0.1 Hz. And case 2, where voltage is 3.5 volts and frequency is 15 Hz. Our objectives: 1. To investigate a brush DC motor model and characterize its nonlinearities present in our system that bound the usefulness of the model. Characterize a brush DC motor using the time and frequency domain identification techniques. 3. Identify the usefulness of the differences between time and frequency domain analysis.
I'll be talking about the methods. Figure 1 shows the experimental setup. You can also see here the instruments used. The data collection involves 3 main parts, as seen here.
Alright, moving on to our results and discussion. Part 1 was finding the regions of nonlinearity within our system. So what we did is we varied input voltage and recorded the rotational speed of the motor, so you can see our data right here. There's a linear relationship and there's a linear fit line that you can see that's put on the plot. However, there are regions at low input voltages and high input voltages where this relationship of linearity is broken, and that is due to the saturation limit and the dead zone. So the dead zone is the small nonlinear response to the low magnitude inputs. In other words, this is the lower limit of linearity for a positive input voltage. So you can see towards the bottom left, at those very low input voltages, it doesn't actually get the motor to start rotating due to inertia and friction within the system. We determined our dead zone limit to be 0.03 input voltage, so anything below this input voltage is considered in the dead zone and not good data to use. This linear relationship between input voltage and motor rotational speed is also broken at the higher input voltages, so at about 7 VDC, the relationship becomes nonlinear and the data plateaus at about 63 revolutions per second, and this is due to saturation, which is suggestive of the maximum motor speed being reached. In part 2, we used time domain analysis to identify our system parameters.
In this section, I'm going to talk about the time domain system identification. On the right, you'll see that the motor constant Km and time constant Tm that we found varies with input voltage. This is summarized at the bullets on the left, and theoretically, these values should be constant with a changing input voltage. This is not the case. We believe this variation at lower input voltages could be due to the dead zone effects as well as the implication of friction. The Km and Tm values were found from the time domain analysis utilizing the step responses that we measured. The angular frequency versus time at different step input voltages were the response used for the motor constant. The steady state angular frequency was captured as a function of input voltage. A linear regression was done on this data, and the slope of that curve is the motor constant obtained. The time constant was obtained using the average of all of the time constants for different step voltages, and this time constant is shown on the figure 5 on the right, where its relation to omega steady state can be seen. You see the motor angular velocity versus time for various voltage values. This is the step voltage value. You'll see that the uppermost curve is the highest input voltage, and with a decreasing omega corresponds to a decreasing input voltage. The angular speed irregularity can be seen if you zoom in on the steady state portion of the step response plotted here. We believe that this is not a physical phenomenon, but rather some signal noise within the system.
There's also some level of vibration in the lab because of the spinning motor, which could affect the encoder measurements.
The experimental step response was found to have a shorter rise time than the model step response. The model step response in this plot here is a red curve, while the response with and without a mass are shown by the blue and the green curve. The addition of a mass was shown to decrease the time, or increase the time rather, it takes for the motor to reach omega steady state, and thus the time constant Tm increased. The steady state speed was constant regardless of a mass being attached, and was the same for the model as well. And we see that the motor constant Km was constant regardless of the mass attached. In this part, I'm going to talk about the frequency domain identification. Here is the measured system frequency response data as a function of frequency. This will be shown on a Bode plot on the next slide. Here's the Bode plot showing both the experimental data in red and the model in blue. We see that at lower frequencies, the model and the experimental data have great correlation. At higher frequencies, however, we see that it is not representative. And in fact, our system model is a first order system, and the experimental data shows characteristics of a second order system, suggesting that inductance has become a factor, which was ignored in the derivation of our system. This is known because the phase lag reaches negative 90 degrees at the corner frequency. Here are the system constants that we found, both the time constant and the motor constant. There are some discrepancies in the time constant between frequency and time domain analysis, but for the motor constant, the frequency and time domain analyses yielded the same value, more or less. One important thing to point out is that by using frequency domain analysis, we have essentially prescribed a range of frequencies for which our model is valid. For low frequencies, we say it's good, and high frequencies, we say it no longer works. This is something that could not be done in the time domain. So returning to the design goal, of these two cases we were presented, we determined that only for case 1 is our model applicable. This is because case 1 is a low frequency region, and the case 2 occurs in a higher frequency region where the model is no longer representative of the true system. Here's a model that we derived based on the experimentally determined Km and Tm values.
So for our conclusions, the first order model is valid at low frequencies, including design case 1 voltage of 2.3 volts and frequency of 0.1 hertz. This is our system equation that we came up with given our parameters. The first order model cannot be used to represent the higher frequency design case 2, where voltage of 3.5 volts and a frequency of 15 hertz. The first order model cannot be used to represent the higher frequency design case 2, where there's a voltage of 3.5 volts and a frequency of 15 hertz. If a representative model is desired for design case 2, then a second order model is necessary.